So now, another very non-controversial topic. Moore's law is really dead, what's next? This is our next panel is focusing on what will be the aftermath of the phenomenon of Moore's law. We're very honored. Our moderator for this discussion is computer scientist and the former president of Stanford University, John Hennessy. John and your panel, please come up.
Thanks. Whatever order you like is fine. So what do we mean when we say Moore's law is dead? Do we mean that transistors will never get faster, will never get more dense? Well, it really helps to go back and look at Moore's original projection. In 1965, he wrote the first paper that actually projected that semiconductor density would increase every year. In 1975, he modified it to talk about an increase every 2 years. And in fact, that rate, that exponential growth rate, was maintained for roughly the next 25 years after his revised paper. And then Moore's law began perhaps what we might call dying, or slowing down anyway. We went from a doubling every 2 years to roughly a doubling every 3 years, sometime after 2000, between 2000 and 2005. And more recently, it's been close to a doubling every 4 years. So we're slowing down. We're reaching the end of silicon technology as we've known it. But there's another key factor here that rarely gets talked about except among people who are friends with electrons, as our good friend Chuck Thacker was. And that's what's called Dennard scaling. Dennard scaling is a property that says that as the devices get smaller, their energy consumption also drops at the same rate. What that meant was for many years, you could get the same square millimeter of silicon to consume the same energy, which made it very easy. Well, Dennard scaling ended actually before Moore's law actually ended and has been sort of non-operational for nearly 10 or 15 years. And that's created another problem, created this so-called era of dark silicon. We all turned quickly to multi-core. We thought that was going to solve all the problems because we didn't have to build faster uniprocessors. And lo and behold, along comes the end of Dennard scaling, meaning that more and more processors cannot run faster because they burn up. Of course, we've all built and relied on this tremendous hardware improvement. It's made it possible to do things like deep neural networks. It's made it possible to build software that uses layer after layer and software reuse, and still not worry a great deal about the hardware efficiency. The hardware just kept getting faster and faster. Now we're in a different era. Perhaps we're entering an era where dark silicon will mean a dark age for computer science. Perhaps it will mean we have to rethink the way we program or rethink the way we build machines. To address this problem, we have a great panel here today. To my left, Doug Berger, former professor at UT Austin, now a distinguished engineer at Microsoft working on accelerating computing in the cloud. Norm Jopi, one of the original MIPS team members some 30 years ago. And then spent time at DeckWorld, HP, and is now at Google working on processing in the TPU arena. Butler Lamson, Turing laureate, who's probably done more work on machines that have changed our lives than just about anybody I know, including inventing the modern, what we think of as the personal computer. Butler is now a technical fellow at IBM, at Microsoft Research. Well, there's another merger coming up here. And also an adjunct faculty professor at MIT. And finally, Margaret Martinosi, a chaired professor at Princeton, who was recently a Jefferson Science Fellow in the US Department of State. And her work is focused on power-efficient systems, a critical issue for this. So what I've asked is each panelist to make a brief opening statement just to get the ball rolling. If anybody has any robust objections to any panelist statements, they can jump on them right away. Then I have a few questions, and the audience is the critical factor in any great panel. So we're expecting you to ask definitely challenging questions here, and the students will be passing out index cards. So let's start with you, Doug.
Okay, so first of all, I'm more of a stickler for the definition of Moore's law as we were discussing today. So Moore's law was about a rate. It got adjusted once about 40 years ago. And if I thought that it would get adjusted again and keep going at that rate for a while, I'd say that Moore's law is alive and well. But to be the precise definition, it's about a rate. And I think we're kind of in the end game of a predictable rate. And there are only so many generations left before we hit really hard atomic limits, and that number is not very many. And it's, the costs will grow quickly. So what does it mean for a 50-year exponential to end? Well, we've been in this exponential for our entire lives. And an analogy I like to draw is global warming, right? We're just in a new regime that's going to be transformational. And we know it's there. It's like a slow-moving force, but we can't attribute any one event to it. So a major acquisition by a semiconductor company, a shift in architectures, consolidation, is that because of the failure of Dennard scaling or Moore's law being dead or dying, depending on where we are in the rate? I think we don't know. But those oscillations are going to increase in amplitude. And I think 20 years from now, the industry will be unrecognizable compared to what it is today because of those oscillations. The computing stacks, architectures, languages will look very different, at least if you have high performance needs. So what should we do? Well, I have 6 approaches. I'm not going to go through them in detail because I don't have time. But there are.
He had 45 minutes prepared, but I.
That's right. That's right. Cut me down 90%.
4 is okay.
All right. So I'll list 3 directions forward, and then I call them the obvious, the ugly, and the evolution, and then 3 new directions: the smart, the crazy, and the wild. Okay. So the obvious is to improve performance within our current paradigms. So mining the fat out of the software stacks, layers of interpretation, as John said earlier today, get our general purpose processors running faster. They're less than 1% efficient. A floating point operation on a modern processor is 30 picojoules, and the instruction to do that is 10 nanojoules. It's a factor of 300 different. So I think there's a lot of opportunity left there, but we're not really focused on it as a community. But that's within our current paradigm. Okay, so the ugly is, I think, an inexorable trend towards domain-specific architectures and stacks. So we're going to create Franken systems with just many, many, many stacks of different silicon, different languages. Okay, and it's going to be ugly, but the industry is big enough now and these are important enough problems that we can accommodate that. So that's going to happen, but it's going to be ugly. And then there's an evolution. I think we're moving to new architectures, and some of my recent work has been towards what I like to call spatial computing. It's not a new idea. It's not, I didn't invent the term, but CPUs are really temporal computing. You have a small working set of data, and you stream instructions through those. And if you're changing that working set out, you're really slow. Spatial computing is the transpose of that. You fix the instructions down and you stream data through. And that's one reason we've made such a big investment in FPGAs at Microsoft, because you could put down these functions or instructions and then stream data through at line rate. And that happens lots of places in the cloud. So that's, I think, a new paradigm. It's hard and it's ugly and the languages aren't there yet, but I think there'll be a lot more of that. And FPGAs are useful because you can actually change the function while things are evolving rapidly. Okay, so then going to the 3 new paradigms, I gave a talk a few years ago at Microsoft's Faculty Summit where I said, well, what's the long-term, what are some long-term opportunities? So one is neural, or AI, deep neural networks. I hate working in hot areas because there's too many smart people. This one feels real, so I'm violating my rule because I think it's really, really important. There's something deep and fundamental here, and we don't really understand it. And so, the CPU performance gains are going like this. Deep network requirements are going like this for performance, and that gap is why we're seeing this Cambrian explosion of new architectures, some of which famously Norm has led. And I think one really interesting thing in that space is that we're doing vector computing, we're doing matrix vector multiply. You can reduce precision, you can make those more efficient, you can benefit from the silicon scaling. That's going to play out over the next 3 or 4 years, and what comes after that I think is a really important question. There's a huge gap, many, many orders of magnitude between that and the brain. So that's going to be a fascinating, fascinating time. And then there's the crazy, so that's the smart. The crazy is quantum. I think the challenge there is the algorithms. I think we'll build them. Can we solve really important problems with them? Is that a general purpose thing or a very specialized thing? I think that's TBD, and it really relies on the theorists and the algorithm people to figure that out. And then for the wild, I think this is the last point, it's programmable biology. That's something that really needs computer architecture and computer science thoughts behind it. So protein pathways leading to gene expressions, leading to protein pathways. There is an architecture there that we don't fully understand. Our understanding is very sparse. getting a handle on that will be really important. I think that's the longest term one, but that's much longer term. So I guess to conclude, I think I'm at time. Moore's law has given us a free ride in performance with existing paradigms for 5 decades and more, and that free ride's just about over. So we're entering a wild, messy, disruptive time, and it sounds like a lot of fun.
Margaret, why don't you take this next?
Sure, thanks. So I wanted to use my time to tell most of you who are not circuits and architecture people why you need to care. And you need to care because it's going to be a wild time, and it's not just going to be the hardware people who are having a wild time here. I think that's very important. We've actually already seen the start of this. Over the past 10 to 15 years, we saw this upsurge in the use of on-chip parallelism, which dramatically changed software already, and will change it much more as we adopt more parallelism within applications. And then the second wave has been the adoption of heterogeneous specialized accelerators on chips, which again sort of pushes things in a new direction and dramatically changes software. So there's something else that's roughly 50 years old besides Moore's law and me, and that is the instruction set architecture. So for 50 years, the deal was that Moore's law was sort of delivering transistors relatively regularly, and hardware people were working hard for you to create faster and faster processors that sat underneath a durable abstraction layer, a hardware-software contract, such that the software above it could get relatively free performance improvements with relatively few changes, relatively little need for porting or tuning. That has changed. So as one contrast, about 25, 30 years ago, processor chips hit a previous power spike in power density. But we were able to shift technologies. That's when that power spike is what drove the CMOS adoption to a large degree. And software people didn't really see that shift, as far as I can tell, at all. Whereas today's shift is quite different because we don't have the good alternatives sort of queued up and ready to splice in. So inside our computer systems today, we're increasingly likely to have many ISAs present. And this is true whether you're in mobile or cloud or anything in between. Your phone typically has maybe 6 ISAs on the processor chip, 6 different processor languages that are being spoken in there, and many accelerators. Half the area is accelerators that have no durable instruction set architecture at all. So what that means is we know how to build the hardware. We haven't come up with good new ways to program it. In particular, when we move from one implementation to another, an awful lot of the software has to change. I call it the post-ISA or post-CPU era, not because we're done with ISAs or CPUs, but because they don't have the durable abstraction, overarching abstraction powers that they used to have. The amount of reworking varies, but it's often pretty broad rewriting of software for new mixes of CPU, GPU, and accelerators, sometimes shielded by libraries or APIs, but someone's dealing with it, and it's not fun. And that brings me to the second big issue, which is about correctness and verification. I mean, we all know how hard it is to get a computer system right, both the hardware and the software. We're increasingly worried about security and reliability as well. And the current technology trends are going to make this much worse because we're building systems that are more heterogeneous, more complex. Major software changes are happening more often as we rewrite things to port between things that don't have good abstraction layers. And the last thing is that because things are changing quickly and because we're experimenting with new technologies, we don't have well-specified enduring interfaces against which to verify, against which to check correctness, check security. And so that is going to create a situation where we're building systems that are harder to keep correct and secure, and yet wanting more and more that we do so. The final aspect of that is, aside from FPGAs, a lot of the other specialized hardware that we're using is baking functionality into hardware in a way that makes it very hard to push out a patch when you find a bug. And so that'll be yet another issue for this security and correctness and verification space. And the third thing I'll stress, and maybe this is where Doug and I differ, is I think that application-driven approaches are kind of cool and not necessarily gross or Frankenstein or whatever you called them. So I think it's an interesting opportunity where instead of sort of the 1975 layering where you had the architects, the compiler people, the applications people with these horizontal layers that we've often drawn, I think we're going to flip it, have these domain-specific slices through those layers where there are going to be DNN people who are very good at sort of reaching down and understanding how the hardware implies something about what they should be doing up high and vice versa. So we need to be exploring design processes that handle that flip well, to be domain-specific, languages and so forth. And we need to be training students who have good skills up and down that stack as well, because if we're going to shift everything about our field and then not think about how the curriculum and the pedagogy should shift, then I think we're going to be in real trouble. So a main takeaway is this technology trend is not super new, although the sort of the end game of it is new and somewhat mysterious still. It's definitely not something the hardware folks are going to solve under the covers. I think that's already been the case. It reminds me of the frog. You know, there's the story about if you put a frog in boiling water, it will jump out. But if you put a frog in lukewarm water and gradually turn up the heat, supposedly it stays still. I don't know. I haven't experimented. But I feel like all the software people of the world, you're that frog. You're sitting in water and it's warming up. Thanks.
All right, great, Margaret. Norm?
Okay, we all feel so much better after that.
Yeah, exactly. Besides, I like my frogs sauteed rather than boiled.
Hardware people are okay. They're turning up the heat.
Yeah, good one. Yeah. So when I saw the title of the panel, Moore's Law is Really Dead, it reminded me of the Monty Python Pet Shop skit where with the parrot, and he's only resting, pining, and lots of other interpretations. I think we still got a few more years, but the way I think about Moore's Law is in terms of order notation. And so if you think about making something more precise in one dimension, that seems to turn out to be linear increase in cost. But for many years, we were getting a free lunch because with optical lithography, we were getting that n factor in 2 dimensions. So we were getting n squared. And when we were having Denard scaling, that was another factor of n in terms of device performance and power efficiency. And so we were getting this n cubed for the price of n. That's really a good deal. But now, some of those factors are starting to go away, and cost will be a limiting factor, I think, before device physics will be. But, you know, it's neck and neck. It's going to be close. So right now, what's happening in optical lithography is if you want to make something finer by a factor of n, you have to have each mask be finer by a factor of n, and you have to have n times as many masks. So your n squared just went away because you're paying for twice as many masks for 2x scaling, and each mask has to be 2x more fine. Okay, so if you think about that, there's many different applications. And so Moore's Law is not going to be a binary event. You can't say Moore's Law ended, June 22nd, on this year or something like that. Instead, it's going to depend on the application. So some applications benefit much more from transistors than others. The classical thing from computer architecture is if you scale a cache size by a factor of n, it reduces the miss rate by a factor of square root of n. So that's if you're dealing with something where you're not getting a lot of transistors and having to pay a high price for them, that's probably not a good thing to have just bigger and bigger caches. Domain-specific architectures, yeah, I consider them a work of art myself, but they're really good, at least the ones that we've done so far, are really good at using transistors. And so if you have n squared increase in transistors, you can get n squared in value out of them. And of course, just like any other system, you can waste the transistors doing needless operations, but you do get that increase in computational capability. So I think we're going to be seeing a lot more domain-specific architectures going forward. I think, if you think about other fields and how they've matured, if you look at aviation, in 1970, the 747-100 could carry 500 passengers at almost the speed of sound. And nowadays, we have things like the Dreamliner, which are much more power efficient. They have bigger windows, all these other things, but it's not dramatically different. But the efficiency is much better. And so I'm hopeful that we'll be able to refine the software as well as both the hardware. I think we've gotten a little sloppy in the hardware design, just racing to keep up with Moore's Law. And I remember the very careful designs we did when we didn't have many transistors. And they are much more efficient than what we have now. So I think both on the hardware and the software side, there's room for mining that efficiency for a long time.
Butler?
I'm not really a hardware person, although I have done some hardware design. I'm here as a substitute for Chuck Thacker, who, as most of you know, probably died a few weeks ago. But fortunately, I've been working with a group at MIT to try to figure out what the consequences are going to be for computing as Moore's law tapers off. And our slogan is, there's plenty of room at the top. This is a play on Richard Feynman's famous lecture, There's Plenty of Room at the Bottom, which he gave in 1959 to the American Physical Society, where he predicted most of the things that have happened in electronics and nanotechnology up to now. So what does it mean? There's software, there's algorithms, and there's hardware that make up the computing stack, and there's room in all three of these above the level of the devices. It's not going to be as good as Moore's law, because in the days of Moore's law, you'd get more and faster transistors down at the bottom, and everybody up the stack could benefit without having to do anything, because the changes were not visible functionally. You just got better performance at the same price, and that's not going to be true anymore. As a result, progress is going to be much more sporadic, much more opportunistic, and much more bounded than it was in the case of Moore's law. And also, as several other people have said, the changes are going to be much more visible throughout the software stack, which is going to have very serious consequences for the way things get developed. So on the software side, we know there's a lot of software bloat because we've been getting away with bloat for many decades. It occurred to us that there's an interesting way to look at it. The theorists like to understand problems in terms of reduction. If you have one NP-complete problem, you can show that another problem is NP-complete by showing how, if you could solve the second problem, then you could solve the first one too, which you already know you can't do. Software people do reduction too. Another name for it is software reuse. Instead of writing a program to solve some problem from scratch, you write a program that reduces that solves the problem using some already existing piece of software, which is usually a cheaper and more reliable thing to do on the development side. But it's definitely going to consume more computing cycles and more memory. And when you stack these things up 10 or 20 levels deep, which we definitely do nowadays, there's a huge amount of bloat and a lot of scope for getting rid of it, at a price, of course, in development cost. Algorithms, history tells us that at least in many domains, the improvements in performance produced by better algorithms have been quite comparable to the improvements in performance produced by Moore's law. But of course, the algorithms are quite problem-specific, and it's also the case that improvement tapers off after a while, often because there's some upper bound on how good the performance can get that you can actually prove. Hardware, the iron laws of physics, as they're currently manifested in hardware, tell you that if you want to get the maximum amount of performance out of the transistors that you can put on a chip, you have to have the parallelism and locality of the computation exposed in such a way that the hardware can take advantage of it. And historically, we've not been very good at doing that. The other avenue for exploiting advances in hardware is specialization, also known as domain-specific architectures. And it's pretty clear that there are very important domains in which you can get a factor of 100 that way, at least. Final thing I want to say is a consequence of the fact that changes are not going to be invisible anymore is that you need a strategy for propagating the consequences of the changes through the software stack. And at the highest level, the only strategy I know for doing that is what I like to call big components. That is, you make a big thing that consists of a bunch of hardware and a bunch of software, and you give it a very stable interface. And then inside there, you can innovate much more rapidly than you could if you had you can make changes up and down the stack inside of the big component much more rapidly than you could if the consequences of changes at a low level had to propagate through the entire uncontrolled software ecosystem. So a good example of that, I think, is the way Google has been doing the TensorFlow thing, where they've defined a high-level interface, and they don't give the users of the chip access to the chip itself. They only give access to this high-level interface, and inside of it, they can evolve things much more rapidly. So to sum it all up, we think there really is plenty of room at the top, both in software, in algorithms, and in hardware. And it's going to take a big component architecture to exploit these opportunities. But I don't think there's any doubt that there's several orders of magnitude more performance that can be gained by pursuing these ideas.
Good, thank you, Butler. So let me start by saying if anybody wants to go out on a limb and declare whether or not there's a silver bullet solution here, it might, or any of these ideas, whether it's die stacking or cross-point technology or quantum, are they about to solve the problem for us and we just have to hold our breath until we get to that magic point?
I did want to say that I know nothing much about device physics in spite of having been a student of physics in my youth. I don't actually believe that Moore's law is dead. There's lots of physical phenomena, it seems to me, that have the potential to make it possible to have higher and higher performance computing devices for a long time to come. But it's not going to be silicon and CMOS. And up to now, silicon and CMOS has definitely been the place to put your money. So people have not worked really hard on these other things, it seems to me. But I'm just talking off the top of my head. I don't actually know anything. Except that there are all these phenomena. I mean, there's atoms and spin and all kinds of cool
well, what do you
stuff
think,
out
Norm?
there.
You've thought about some of these things, and Margaret, I know, has done some work on quantum. Either?
Yeah, Doug and I were talking earlier about how much fun we're both having at work, and we didn't think we'd be having that much fun a decade ago. Because, sorry, there's so many different novel things to look at, and that they can all play a part in the overall solution. It's not a silver bullet. There's a lot of things that we should be investigating and benefiting from.
You were so sad 10 years ago. I'm sorry. I'm really happy to see that you're happy.
What about quantum, Margaret? I know you've thought some about this issue as well.
I'll say something about quantum, but I wanted to react a little bit to what Butler said. So Moore's law, as we all know, is not a law of physics. It's a business or economic law.
It's empirical observation.
It's about will there be reasons to keep pouring money into a process to maintain a doubling? And so while there may be physics still to tap, the question is at what cost will it come? And can we find physics that reaps enough revenue benefits to warrant the investments?
Right. Yep.
So that's that. You prompted me for quantum, and it's been close to 10 years since I wrote my first paper on quantum, but I keep it sort of a side thing and a little bit secret because architects traditionally work on things that are sort of very real, and quantum 10 years ago was kind of a weird thing to even work a little bit on 10 years ago. And so the good news is that I think quantum computing today, from a physics perspective, is amazingly close to being real. There are folks at Google and other companies who say that a 50 to 100 qubit machine, in terms of the physics, will be available in the next year or two. There are even people who say that they will write programs for that 50 or 100 qubit machine that will show speed up over classical, which is the so-called quantum supremacy or quantum advantage point. So that the physics side of the story for very narrow problems is starting to become credible in a way that wasn't true for many years. The harder part is that the applications, as sort of applications that one could run on a 50 or 100 qubit machine, aren't there. There's a huge gap between the number of qubits you need to build viable, interesting applications using the quantum algorithms that we currently have, and the number of qubits that the physicists will be able to build into reliable operational systems anytime soon. So that's one issue, is this gap between qubit counts that we might want and qubit counts that we'll get anytime soon.
Will it still be good enough to wreck public key cryptography?
The likely outcome that many people feel is that we'll come up with quantum-resistant crypto and make that somewhat moot. It'll be a while before it can wreck public key crypto. That needs more qubits, from what most people say. The second thing is it won't be general. It'll be in a coprocessor role. But many of the things we're talking about are in coprocessor roles. And I guess the third thing that gets back to this law of physics thing is Moore's law was sort of amazingly providential in the way that we came up with many, many intermediate ways of making money off of transistors that caused that doubling cycle to sustain itself over 50 years. Mm-hmm. And the people who are thinking hard about how to create Moore's law for quantum computing are having trouble thinking about what might be those intermediate points. When you get past the kind of Sputnik or moonshot kind of initial bragging rights on 50 to 100 qubits, and you try to move from there to 10,000 or 1,000,000 qubits, there's an awful lot of money and engineering that will need to go into those phases, and the path isn't clear for who would pay and for what applications, I guess.
Norm,
And there's another panel tomorrow morning, so they know more answers. Yeah.
Norm, you touched on the cost issue with respect to lithography, but there are lots of other cost issues, and part of what's causing this slowdown is the cost of fabs is just going up by leaps and bounds, and the number of fabs in the world is shrinking dramatically as a result. I mean, do you think that this becomes the actual barrier, that simply you can't afford to build many advanced fabrication capabilities?
Well, Doug was mentioning the consolidation earlier, but
Yeah.
I think, as long as we have 3 or 4 stable players, I think there'll be good competition. And, like with a new iPhone every year, they have to have a better chip in it, and so there's a lot of market pressure to come up with the next best thing.
There's also a lot of price pressure on the cost of that iPhone, so they've got to also be able to build it cost-effective. So Doug alluded to the Franken architectures as a way to describe this meshing together. I mean, it's clearly the case, I think, as several of you pointed out, that a heterogeneous computing model is certainly more complicated from the viewpoint of verification, from the viewpoint of software. Is this going to fall as a giant burden on programmers, or are we going to come up with some magical software technology to sweep that away? What do you think, Butler?
If it's not going to fall on the programmers, where is it going to fall?
Yeah. Well, maybe there's some magical technology that can do the mapping somehow or extract.
The Fortran of heterogeneous computing.
Yeah, something, or some high-level thing that can extract the structure. I mean, to some extent, TensorFlow is a step in this direction for a limited range of applications, right?
Well, I think all of these things are for limited ranges of applications. The whole nature of heterogeneous, of domain-specific architectures is they're for limited domains. That's what it's all about.
Right. So then where is the burden of, I've got this giant piece of software with multiple levels in the stack, lots of software reuse. Somewhere in there are some pieces that can be sped up.
It's the big component story. You have to find something that you can wrap in a stable interface.
Yeah.
And if you can't do that, then all you can do is proofs of concept. You can't do anything real. That's an absolute requirement.
Right. So does this mean that the range of potential applications will be rather limited? I mean, Doug, you started by mentioning deep neural networks. That's obvious one. GPUs is another. Are there lots of these
deep neural networks is not an application. Yeah. Self-driving cars is an application.
Domain. Yes, domain.
I think one important thing with DNNs, and Norm, I think, should comment here too, is that they're surprisingly general. Like they've moved into lots of different domains. Not the same algorithm, but the class. Back when people were doing speech and vision and this and that, they were all different classes of algorithms that had been tweaked over the years, and the deep networks just kind of swept through and replaced them whole hog. Yeah. So there's something very, at the risk of making a pun, deep here. Yeah. And we don't yet have the von Neumann architecture for deep learning. But I think that's, if we can find that or come up with that, that's a huge direction forward, because this is a very general thing. I think that's why there's so much energy and yes, hype, but also momentum behind the field right now.
Yeah, I think it is one of the biggest nuggets in the domain-specific architecture area, because it can do all those different things. But I think what your question, John, was actually similar to the original Moore's Law paper, where Moore said that he didn't think there was a market for a calculator chip or this or that chip, but he could build a microprocessor, and the microprocessor could be programmed to do all those different applications.
Right.
So some application areas or domains will benefit from this, and others might not. So I think we're going to get more inequality in terms of application speed up. And then I think another thing, going back to what Margaret was saying with all the different components, is it's also easy to get Amdahl's law bottlenecks between the different components. So it's a system architect kind of problem as well.
Let's hear it for architecture.
So it is a system problem, and so then the question becomes a question of where is the bottleneck in this? Is it the programmer's problem? And we're going from an era where basically people just wrote code. I mean, look at how much energy went into taking the x86 architecture and making faster and faster and faster versions of it. So we didn't have to touch the software at all, right?
Well, so one thing I'd like to comment on, harkening back to the previous panel, is there was a lot of talk about data preservation and well-specified interfaces and ways of describing. And sorry to toot architects' horn, but I think we did that, right?
Better than anyone else.
Better than anyone else. x86 is, what, 47 years old now? It's,
Yeah.
and
it's unbelievably complicated, but it's actually
and it's
kind of
still
well specified.
executes.
Yeah.
So the failure for code to run year after year is because of other parts of the system we didn't specify to that same degree. The operating system, the I/O interfaces, and so forth. This notion of specifying interfaces well and then building around them is a very powerful one.
Unfortunately, programmers hate it.
Yeah.
But they're going to have to learn better. There's going to be no alternative.
Yeah, if you want to get faster, you're going to have to do it. All right, let's take a few of these questions because some of them are quite provocative. This is a great question for you, Doug. Are FPGAs a fundamentally important computing device or just a crutch for companies and engineers without the courage or skill to build custom
Or
chips?
foolishness.
Okay, the A+ question here.
I want to come back with something witty, but my mind is just blank at that comment. I draw a graph sometimes when I give talks on this, and on one axis is the rate of change of the algorithm, and the other axis is the proportion of workloads in your cloud device family that the accelerator can benefit. And if you look in the cloud, you have tens of millions of customers. It's just an incredibly general purpose thing. And even the big properties don't run on more than 1 or 2% of your servers. And for the big online services like Bing and Google Search, they're changing weekly or monthly.
Right.
So that's just really tough. And I think that's even too fast for the FPGAs, but you can at least get a handle on some of that and upgrade your algorithms. So I do think there's something general there, but they're still far too hard to program. I think and we're making progress and the effort is coming down, but the barrier is still too high to make it really general.
So they really do give flexibility. Norm, what do you think? Because you've gone the custom route rather than the FPGA route.
Yeah, but so I think the custom can tackle those big nuggets, but the tail is basically wagging the dog in many of these data centers, and so I think FPGAs can be really useful there, as that almost like a microprocessor for those applications. It's something that can be programmed differently.
Maybe just to follow up on that, there's a three-part, 3 segments to that curve. There's the stuff that's running at really large scale and stable. You harden that. There's the stuff that's changing too fast or is too small scale to justify the NRE to put on an FPGA, and better tools bring that down. And then there's the stuff in the middle where the economics work, and you can and so those 3 buckets are sort of changing in size.
Yeah.
And so we'll see what happens.
Yeah.
All right, this is a perceptive question. Margaret speaks of turning the traditional stack of horizontal layers on end, but my experience, says this questionnaire, over the past several decades is that fewer software engineers have the requisite deep vertical background that this would require. Haven't we been teaching and moving in the wrong direction given this change that's upon us?
So aside from our esteemed moderator, I'm actually the only academic here. By the way, don't believe the hard copy brochure that says I'm at Google. I'm not at Google. I'm at Princeton. I like Google, but we're just friends. So I think we need to tell the story of these verticals in a way that lets students see the impact of the full set of systems design challenges. They see the application layer just fine. That's all around them, and that's what they're drawn to, and that's great. It's wonderful to see. But they need to know that cloud computing doesn't run on actual clouds. They need to know there's hardware under there that someone has built. And I think sometimes in some departments they've lost track of what's sort of supporting this massive revolution.
It's extremely difficult to keep it on track. I mean, MIT tried very hard for a long time, and they're gradually giving it up because you just can't get the students to pay attention.
But isn't this partly because our field has exploded by leaps and bounds? I mean, you can't imagine having a student that doesn't have some exposure to machine learning now as part of their undergraduate curriculum. And everything they've got to learn is just blown up by leaps and bounds. How do we get them enough knowledge about the lower levels of the system, including the software levels, so that they have a better understanding and still get it done in 4 years and have them graduate rather than drop out because we burn them out?
So I think we have some nice examples of textbooks and classes that merge some hardware and software into a single sort of systems-y oriented class. I think that's one avenue. Another avenue is that as they're learning about DNNs or other sort of more application-focused topics where they're flocking to, making sure that there's enough of the underlying support systems built into those classes as well.
So one question here is, what is the impact of Moore's Law on Frasers Law, which I wasn't sure what Frasers Law is, but luckily it's defined, which says that the cost of computation drops by a factor of 10 every 5 years. So are we going to see the computation improvements in terms of cost of hardware? We are used to hardware dropping, at least in cost, or getting faster for the same cost. Are we going to see that slow down and end?
I think it depends on the application area.
Yeah.
So some application areas, I think it'll continue for the next decade, but other applications, it's going to be very slow and very small progress.
I guess I don't need my cell phone to run faster because I can't speak any faster.
Actually, video is really good at sucking up
Video
the
will.
transistors.
Video sucks up.
Also, I think this isn't the right way of saying it. What people actually care about is that the cost of running the application they care about is dropping.
Right.
That means that improvements in software, improvements in algorithms, as well as improvements in hardware can all contribute to that. And that was kind of the point of the story about there's plenty of room at the top.
So talk about this efficiency issue, Butler. I mean, I think if you look at a large software system running on a modern piece of hardware, whether it's in the cloud or on a big server, the inefficiency is spread all over the place. There's certainly inefficiency at the top with multiple levels of software, especially if they're writing a scripting language or something else. But there's lots of inefficiency in the underlying hardware and in the exact interface between that hardware and software. Do we have to go on an expedition to mine that inefficiency out piece by piece in order to really get the kind of performance we need?
I don't think we really know because except in certain fairly specialized domains, the motivation has not been there to really dig into this question. The most that people typically have been willing to do is to try to make better compilers. But I think we have a lot of experience by now that tells us that that's by no means sufficient.
No, it's a hard problem. We haven't made the quantum leap that we thought we might get in compiler technology.
And we definitely haven't dug into it seriously, in my view.
And it's also easy to lose a lot of performance in large-scale distributed systems, and so, yeah.
Although that's certainly a domain where the limitations of Moore's Law are by no means so compelling. I mean, there's been so much fat in the hardware and low-level software that run distributed systems, the communication part of distributed systems. We're gradually learning how to take that fat out, but I think there's still a lot of opportunity there.
Yeah. Here we have a question. Current commodity architectures are very problematic from a time predictability point of view. The worst case, the execution time can be considerably worse than the best case expected time. Are there any hope that the changes to come will enable better time predictability in terms of computation?
Depends on the application.
I think this is where specialization really makes a difference. So you can build a very deterministic specialized pipeline for an application. You get great performance predictability, but you lose generality. You spend all this time building it. All those caches that we like to complain about give us generality, and then they just make predictability terrible. So if you could merge those two and have great predictability and great general purpose performance, you'd be in great shape. But that's kind of that's a holy grail that doesn't exist.
Predictability often involves designing for a tail, And
Yes.
architects like to make the common case fast. And those
Right.
are distinct.
Caches work great when they work great, and when they don't, they're a disaster, right? It's the classical kinds of
Yeah.
problem.
But in some domain-specific architectures like GPUs and even in the TPU, I mean, we don't have caches. So.
Right,
Right.
right. New CMOS-compatible devices are coming, example, TFETs and 3D stacks. So the hypothesis from this question is that the evolution will be gradual. There'll be no big crisis, no big changes will be visible. Is this simply too optimistic a viewpoint? Yes.
Yeah.
Or is it the silver bullet, maybe?
No.
Too optimistic, Norm? You think?
I mean, I think some of those things will work out, but it's going to be a long, painful process. I mean, if you think about when different gate dielectrics were introduced, they thought it was going to be at like 90 nanometers, and it wasn't until like 45 or something because there were reliability problems. We were seeing the same things in non-volatile memory technologies. People thought they had it down, and then the error rates were higher, and endurance wasn't as good as they thought. And so these new technologies are often more difficult than they appear.
So what about, we haven't talked at all about DRAMs and memories, but DRAMs are really near the end of their lifetime as we know them, right? They're really near the end. The prediction rate, the next DRAM just got shoved out another year before it's ready, and there is no path after that next revolution in DRAMs. So we're not going to have memory capacity. How are we going to deal with that? It seems like we've used DRAMs to hide a lot of sins in terms of the amount of memory we use. What happens when you don't get any improvements in DRAMs?
It unbalances the architecture. And so it's yet another thing where these things are improving at different rates, and that will contort systems. So it's a full employment offer for system architects.
Yeah.
Right? Every
But also
imbalance, you need to re-architect the system.
But also, I've a little bit lost track of what's been happening in the last year or two, but there's no doubt that if you look at technologies like Flash, they were originally deployed to store pictures in cameras, and the interfaces that were provided to the basic technology were incredibly poorly suited for computing. And it's been because the camera market was much bigger than the computer market for Flash initially, it's been a fairly long, slow process to fix that. My belief is it's still the case that we by no means have the best possible interfaces to the Flash. Right. So it may well be that the fact that DRAM, it'll be okay to just treat DRAM as a terabyte-sized cache and integrate it much better than we currently do with the next couple of levels up, which don't have the same gigantic gap that we used to have between DRAM and disk.
Yeah, and speaking of silver bullets, I think vertical NAND is the closest thing that we have to a silver bullet because Flash was supposed to stop scaling at 20 nanometers, and now we've got 64-level vertical NAND Flash that's coming on the market.
So you're betting on vertical NAND Flash rather than some kind of cross-point technology?
I think you need to put your money on lots of different things.
Yeah, right. You'll take what you can get.
Yeah.
Put your money on every number on the
Yeah, right, exactly.
That'll work out well.
Then the house wins, right?
That's right. House always wins.
But your winnings are less when you win. All right, is there a place for portable high-level languages in the world of domain-specific architectures? And if so, what might those languages look like?
So yes, I think there is some really interesting work pushing on domain-specific languages. The Franken camera work out of Stanford is one nice example of that, and automatic compilation down to different and diverse hardware platforms. I think the best hope is actually to go for the domain specificity at the language level and then have it manage the heterogeneity that's under the covers down there. So I think that's a huge opportunity going forward to have the applications be specified in something that's high level and somewhat agnostic to what's in hardware or software or what kind of hardware or software, and yet specific enough to the application that the compilers can actually get some traction on mapping it to real hardware.
Now, the canonical example of success in this domain has been query languages for databases over the last 30 years. We should all aspire to do as well as that.
Yeah, so it's possible that some of the sort of interfaces that we think about won't be languages in the way we've thought about them in the past, but more environments, interface environments under which everything is compiled.
So, Butler, what about moving up the software stack? It seems to me there's been this tension between functionality and performance, efficiency, however you want to think it, and for the past 30 years, functionality has triumphed. Functionality has even trumped correctness often. Right? More important to get it out there even if it doesn't work quite right.
The slogan is worse is better.
Yeah, exactly. So do you think this will change, or will there really be a lot of pressure on the companies to get new functionality out more than to get it to work efficiently or to get it to work correctly?
Depends on the application.
Yeah.
I like to say there's two kinds of software which I call precise and approximate. Precise software has a spec, whether or not it's written down carefully. And if you don't satisfy the spec, the customer's unhappy. Approximate software has no spec. There's no spec for Facebook or Google search. It just doesn't make sense to think in those terms. It's not that one kind of, computer scientists tend to think that, of course, precise software is better for obvious reasons. My view is both kinds are just fine, but it's very important to know which kind you're writing. Because if you are writing approximate software and you think it's precise, you're going to do a huge amount of engineering that your customers are not going to appreciate. And the other way around, your customers are going to be pissed about the fact that the software doesn't work. But the whole reason the web was such a success is that it doesn't have to work. Right? And it doesn't work. My personal experience is when you click on a link and there's at least a 1 or 2 and maybe a 5% chance that the wrong thing happens. And it's also true that if you click on it again, there's maybe a 30 or 40 or maybe even 80 or 90% chance that it'll work the second time. But the whole thing definitely doesn't work, which is not a criticism. You think it's a criticism, but it isn't.
But wait a minute. I get to my bank account through the World Wide Web these days.
Well, that's a particular application of the web that's been done. I'm talking about the web as ordinary people experience it. They don't distinguish the internet part, the HTTP part, the server code part, yada, yada, yada. You're distinguishing those things.
So is
the
AI
bank is going to be much
software,
more
where does
conservative.
AI software fit in this?
Depends on the application.
Okay, good. That's a good answer. If it's a self-driving car, it better be precise about knowing where it is and the other
Your
cars
bank
on the road
account
are.
looks like this.
And there's plenty of other software that's precise. Excel is precise software. People are very upset if the numbers are wrong.
Yeah, true.
But it's hard to predict where your software, where your systems are going to get used over time.
That's true,
for example, underneath the covers of the IV machines in your hospital, there's typically some Windows XP running. Let that sink in, right? So did they intend for that to be on one side of the precise, non-precise line when they wrote it and then it shifted?
Windows is definitely precise software. It doesn't mean that it always does the right thing, but it does have specs, and people get upset when the specs aren't satisfied. Windows is definitely
supposed to be precise software. Is what?
No. This is a way of thinking. This is the way of thinking. Does the software have a spec, and does the customer care about the spec?
Yeah.
It has nothing to do with how good a job you did of building the software.
Good.
I hold no brief for Windows XP, by the way. I had nothing to do with it.
I know.
But it's an easy thing to snipe at it, and I don't think that's particularly sensible.
It's unsupported. So, I mean, to have an IV machine in today's hospital
Well,
running,
whose fault is that?
Right, but that's my point, is that people are sort of glomming these things out of other things in a way
sure,
that
of course, of course.
design.
And software lives a lot longer than
Right.
anybody ever thought it would live, right?
My favorite story is once upon a time there was a 370 that was running in 360 mode. The 360 was running in 7090 emulation mode. The 7090 was running in 704 mode. The 704 was running a program that emulated an IBM 650. And the IBM 650 program was emulating a CPC, a card program calculator. And down in the bowels of this thing, cards were flowing through simulated cards were flowing through the simulated calculator, doubtless much faster than the 150 cards per minute that they ever flowed through a real one.
Yeah. And it was precise, too.
And it was, so this is both horrible and amazing. Right?
Yeah, it is amazing. It is amazing. It is amazing. All right. So we've said here that domain-specific architectures may be a big part of the way forward. Can any of you identify a small number, say 3 applications, 3 domains, that would account for a significant amount, say 30% of the world's computing load?
Well, GPUs probably already do that.
Well, they're not 30% of the world's
If you measure floating point operations executed, they probably are.
Floating point operations they could do, or floating point operations they actually do?
Even actually do. When there's 100 million Sony and Microsoft gaming consoles out there, many of them being used pretty heavily. They're doing a lot of floating point.
Yeah.
So
It's not a very sensibly posed question. Because, as is demonstrated by the
Does the person
fact
who
that,
asked this question want to raise their hand, please?
as is demonstrated by that I just got to
right, that one
reinterpret it
fails.
plausibly.
I thought it was a pretty good question, actually.
Presumably you don't like my interpretation.
No, your interpretation's okay.
From a user perspective, aside from web browsing, I don't think so. But if you look in the cloud as an example, if you just take software-defined networking, the amount of processing you're doing, just if you're running it in software on a CPU to follow those protocols and rewrite those flows, it's an enormous amount of computation.
Yeah, I mean,
It's a
I think
workload, not an
if you take your
application.
cell phone apart, I'll bet
Yeah.
you there are more cycles in your cell phone devoted to running the cellular network
That's
and
right.
running Wi-Fi than there are even in the GPU.
That's right.
And
Right.
there's special image processing pipelines. There's a lot of different ISAs in there. So.
Right.
Yeah.
Right.
But that's
So
that's
there's a lot
already
of-
hidden. So
A camera, same thing. Camera,
Yeah.
right? You're taking a video with your cell phone. You're doing enormous numbers of operations. So
the depressing point about that is kind of the low-hanging fruit's already gone.
it's already done.
Yeah.
That's maybe the interesting.
Well, software-defined networking is an interesting example of DSAs in reverse. Things that used to be done in hardware are now
are
done
being
in
done in
software.
software.
And now they're being moved
Policies
back into hardware
moving
and
into
the data
software.
Yeah, well, that's the wheel of reincarnation.
Yes, that's right. That's right. The wheel on the data center keeps on turning.
All right, let's see. I need another all right, if a big part of the future of information technology is the cloud, and if the future of computer architecture is domain-specific architecture, will server chips of the future be more likely to be designed by cloud companies or chip vendors? Given that we're turning the entire stack on its side, are we going to re-verticalize the computer industry? After we basically had a vertical computer industry, we turned it into a horizontal? Are we going to re-verticalize it?
I think the answer is yes. So a little bit of both, right? So, I mean, these domain-specific architectures connect to servers, and so they use traditional server CPUs, and so they don't, it's very expensive to offload the whole problem. There's a lot of random code and little things that have to be taken care of. So I think there's a place for both. I think it's a flowering, this Cambrian explosion where you get more and more diversity. So some will be done by, traditional silicon vendors and others by cloud providers.
But will Google design its own RISC-V chips and stop buying x86 chips? He can't say.
I mean, one thing you can say is that we consolidated on a few processor vendors in some ways for ISA reasons. And so if x86 doesn't dominate, if ISAs don't dominate as a reason to buy a particular company's chip, then you could imagine this spreading out over more different companies.
Well, this is the whole idea behind RISC-V, right?
Mm-hmm.
Well, then I guess the counter-argument is there's a whole lot of specialized expertise, let's say, in the chip design component, portion of the job, and that concentrating that in a single company which supplies multiple vendors then is more cost-efficient in the long term.
Maybe that company is called a foundry.
Yeah, well, then it's just a foundry, and doesn't add any value in terms of higher level
But I think,
silicon.
for example, the architecture teams at Intel and other microprocessor vendors are very large for that reason you just mentioned, because diverse applications, they've studied many, many different ones, and they create a lot of complexity at the system level. And so getting that experience is important for building a high-performance microprocessor.
Yeah. It's incredibly hard and incredibly expensive, and yet the
Huge teams.
server market is consolidating on the cloud vendors, which are growing very large. And so how those two forces play out remains to be seen.
Okay, since we have about a minute left, I want everybody's final robust and aggressive thought about the future so that the audience goes out full of energy. Doug?
Put me on the spot. Well, Frankenstein's monster was misunderstood. As a rebuttal to Margaret, I don't think it's a bad thing. I think we're going to see the neural stuff really blow up. I think the hype is, at the risk of being at the top of the hype curve, I think it's real.
Norm?
And I think domain-specific architectures are a work of art, whether they're ASICs or whether they're FPGA-based. And the party's not over yet. The parrot's not dead.
Butler?
You already heard my final thought. There's plenty of room at the top.
Yeah, plenty of room at the top. Margaret?
I think we didn't talk about storage at all. And in a world where we're generating data at vast rates that are still exponential, and we need to come up with better storage technologies as well. We talked a lot about compute, a little bit about memory. The storage thing is fascinating.
DNA will save us.
Hopefully.
Yeah.
Right.
Okay, thank you all for your, are we out of time? We're out of time, yes.
Yep.
Thank you all for your attention. Thanks, panel.
It took away 15 minutes of our scheduled time. It's supposed to be